Okay, so last time we were able to obtain bounds on the probability of a random variable being too large based on the variance, or based on the moment generating function for, say, a Gaussian, for example. But many random variables we're going to better control than what we could do if we had the variance. But we won't know as much about them as we know for Gaussians, right? And so what we're going to focus on is now on trying to capture a large class of random variables for which we don't understand them as well as the Gaussian, right? And we want more control than the variance. And it's really useful to think of the general class of random variables as the sum of independent random variables. It happens all the time in data science, signal processing, and so on, that somehow the random variable that you obtain, you have to control maybe the error on an algorithm or something like this, is obtained by summing many, many different errors, right? And oftentimes these kinds of things are independent, or at least mostly independent, and we really need to control sums of independent random variables, right? And so that's what we're going to do today. So let's take x1 through xn. There'll be, let's say, IID random variables for now. IID random variables. And let's say they'll have mean mu, xk, mu, and variance sigma square. Okay. And let's say we want to understand their sum. Okay, so what do we know about the sum, right? I'm sure in probability class you've seen a few things about the sum, right? One maybe more, the simplest one you can say is the law of large numbers, right? The law of large numbers states that the sum over n, right, the mean, the empirical mean converges to the actual mean almost surely. Okay? Right, so this is nice. So, if you take many, many draws, independent draws of a random variable, then the empirical mean converges to the mean. But oftentimes you're going to need non-asymptotic results. So we need to have an understanding of how fast it converges to the mean, how close to the mean it is, right? As n goes to infinity, because we're going to have high dimensions going to be large n, but not infinite n. It's going to be large. We need to understand errors depending on n. Right, and of course, Sn over n is still a random variable, right? We'll still have some randomness in it, right? Or at least Sn will. If it's converging to mu as I divide by n, it's sort of because I'm dividing by too much, right? Somehow, if I zoom in this random variable more, I should be able to still see some kind of distribution, right? I should be able to still see some randomness in it. And this is exactly what the central limit theorem does, right? I mean, how would you see how much you need to zoom in? You would compute the variance, right? What is the variance of Sn? The variance of Sn, Sn is the sum of independent random variables, so it's just the sum of the variances of each one of them, right? And so this is simply, n times sigma squared. Okay, so now you kind of see why you expect that when you divide by n, everything goes away, right? Because this means in particular, right? In particular, this means that the standard deviation, so the square root of the variance, right? The typical size of the deviations of Sn, square root of the variance, is smaller or equal than, right, root n times sigma. Okay, so sort of you expect the deviations to be of size root n, while, if you're dividing by n, of course, they won't be able to see any of this. But there is another theorem, which I'm sure you've seen too, which is the central limit theorem. It essentially tells you that if you normalize the right way, that you have Sn minus, you take its expected value of Sn, and now you divide by the variance of Sn, right? That this will converge in distribution to a standard Gaussian, right? That it doesn't really matter the distribution of each one of the x's. This will always look like a Gaussian, right? I mean, sure, the first time you've seen this, you probably found it surprising. It is kind of a, impressive statement. And if you haven't seen the proof of this, I mean, try to prove it, right? One thing you can do is try to understand the moments of this random variable, and try to understand that the moments of this random variable as n goes to infinity start looking like the moments of a Gaussian. Right? It's a very nice exercise to try to do this. Okay, but what this tells us in particular, I mean, in computing the variance, right? I mean, we can write this. Maybe it's useful to write this as, right, Sn minus mu n over, sigma root n, right? This is what we have here. Okay, but this tells us that the deviations, right, deviations of Sn should be of the order of, O of root n, right? Or should be of the size, should be of size, I usually use this language, should be of size O of root n. And we can actually see this with Chernoff, right? If we use Chernoff, not Chernoff, sorry, Chebyshev. If you use Chebyshev, we can sort of see this, right? Because if we look at the probability with Chebyshev that, Sn minus mu n, right, minus its mean, is bigger or equal than t, right? We get smaller or equal than the variance, sigma square n over t squared. Right, this is just what Chebyshev gives us. If we do a change of variables, right, we can make make the n and the sigma show up over here. What can we do? We can write it's bigger or equal than u, right? We just make t equals to u sigma root n. Right, so the probability that's much bigger than root n times the variant times the standard deviation of each one times some u is smaller or equal than 1 over u squared. Right? So we get that the deviations are never much bigger than sigma times root n, and this is what we call an unasymptotic. Right? This is sort of an unasymptotic in the sense that it says something for finite n. Right? It starts being more and more interesting as n grows, but it already says something for finite n. But it turns out many times this is not going to be enough. Okay, so sometimes, or many times even, I would say, many times, this isn't quite enough. Okay, so let me give you an example of a time in which this is not enough. Okay. So in the live lecture, we sort of worked this out, all together for a bit. Here, I'll leave it more as homework because it's the kind of thing that you should try to think about it, right? And it's hard to do, interactive version of a recording. But take a matrix A to be an n by n matrix with plus or minus ones as entries. Okay. Okay, deterministic, right? It's deterministic. Now take x, a random vector whose entries are IID satisfying the following. xk is plus 1 with probability 1/2, minus 1 with probability 1/2. And now the goal is understand the infinity norm of AX. Right? AX is now a vector. I want to understand the largest entry of this vector. Okay, so, try it. So pause the video here and try to think about it before you resume. Okay, so now that you've thought about it, maybe one thing that you might have tried to do is to try to understand the probability that the infinity norm of AX is bigger or equal than some t. Okay. And one way that we could do this, right? Let's write it out what this is. This is the probability, right? That the maximum over k in the numbers from 1 to n, right, of a x entry k, right, in absolute value, say, is bigger or equal than t. But the maximum being bigger than something is the same thing as the probability that there exists a k such that a xk is bigger or equal than t. But now, take for each k, this is an event. that this thing is bigger than t. We're just asking that there exists one of these. So we're asking about the union of events. And so this is small or equal in the union bound, or via the union bound. This is small or equal than the sum for k from 1 to n of the probability that ax k is bigger or equal than t. Okay? But now, the distribution of the number axk doesn't depend on k, right? It doesn't depend on the entries of a, because if a says plus or minus, right, the x says plus or minus at random with the same probability, right? So it's completely invariant. So this doesn't depend at all on the row, on which row of a we're taking. All these probabilities are exactly the same, and all of them are exactly the same as if the row as taking the row just of all ones. Right? And so this is actually equal to n times the probability, right? That's we could take the whole one's vector, bigger or equal than t. Right? But now what this is just the sum of xk. So we're exactly in an Sn type situation. Okay? But now try to work it out. Right now, because we're in this kind of situation, if we were to use Chernoff, what would we do? This would be smaller or equal than n times, right? And let's see what we would get. Right, sigma is, okay, we could do this t here. So sigma is 1 because each one has variance 1, right? And we would get n over t squared. So we'd get n over t squared, right? And this would be equal to n squared over t squared. Now, I claim that this gives us nothing. Okay? Why does it give us nothing? If t is smaller than n, then this probability, this number here, if t is smaller than n, right, then this number here, if t is smaller than n, this number here is bigger than 1. And we're just saying that the probability is smaller or equal than a number that's bigger than 1. Of course, it's smaller or equal than a number that's bigger than 1. This told us nothing. Right? However, if I pick t bigger than n, then maybe this probability is telling me something, right? On the other hand, think about what ax is, right? You were just taking a vector x and taking the inner product with the row of a, right? It's just two vectors with n entries of plus or minus 1. So of course their inner product cannot be bigger than 1, right? It cannot be bigger than n, sorry, right? And so just by Cauchy-Schwarz, so always for sure, the infinity norm of ax could never possibly be bigger than n, right? And so if you pick t too small, we're giving a bound on probability is completely vacuous. If you pick t too big, you're also. So in this case, this bound just gives us nothing, right? It's sort of completely, uninteresting bound. And why? It's because we had to, right? We had to union bound over n things. And somehow our tail was not strong enough to be able to union bound over n things. And so what we need is we need to get a bound on the tail that is strong enough, right? If we get some kind of exponential bound such that when we have to compensate for union bounding over many things, still we get a very small probability. Okay, and this is what we're going to do next.